Okay, so we're gonna start our today's seminar, which is co-organized with the MS. Okay, and in this week we're very glad to have Professor Han Xue from University of Arizona, and his topic is local gangrous Prasad conjecture for real unitary groups. Okay, let's welcome Han. Okay. Okay.
So thank you very much for the invitation. Well, in fact, this is the first Zoom seminar I ever attend, and so this is I have no experience with this, and hopefully this goes smoothly. Well, let's see. So I'm going to talk about the local gangrous Prasad conjecture for real unitary groups, as shown here on the title, and it is my honor to be speaking in front of many experts here. And we're going to see that well, many names in this department will appear in the talk, and it is my honor to to speak in front of. Right. So let's start from the very beginning. So I'm going to talk about the classical theorem, the classical Wiles branching law, and I'm going to explain what the conjecture is, and finally I'm going to present a proof. Well, hopefully the proof is short enough and simple enough so that you can follow. Now, okay, so what is the classical branching problem? Well, the classical branching problem is the following. So let's denote this UN by the compact unitary group in n variables. So it's a compact unitary group, and pi is a irreducible representation of UN plus 1. And now we ask, what if we restrict this irreducible representation to UN? Well, of course, UN is naturally embedded in UN plus 1. And of course, this guy is not necessarily irreducible, and well, it decomposes. And the question asks, well, how does it decompose? Well, this question is addressed by the branching law of Weil, and so here it is. So we know that, well, the irreducible representations of the UN, they are parameterized by their highest weights. So it's a bunch of integers like this. And so let's say pi, it's a irreducible representation of UN plus 1. And so it corresponds to a bunch of integers, an to a1 to an plus 1. And sigma is a irreducible representation of UN. And so sigma is correspond to another set of integers b1 to bn. Now the branching law of Weil says that, well, if we restrict pi to un, first of all, it is multiplicity free. So it is a multiplicity free direct sum of irreducible representations of un. And moreover, the sigma, which is a irreducible representation of un, it appears in this direct sum if and only if the following branching, this branching rule. If and only if let's say a1 with bigger or equal to b1, and then a2, then b2, and a3, and then b3, and finally bn and an plus 1. So that's the classical branching law of Weil. So now, well, of course, the question is, well, what if the unitary groups is not compact anymore? So, well,
Xiaohan, actually, very simple question. Actually, this particular formula, I mean, where does it occur? Is that Weil's classical group book or the other book on quantum mechanics? I mean, I haven't seen, you know.
Yes.
I mean, explicitly, does Weil actually say that? Or, I mean, no, it's a consequence of Weil's
I'm
formula.
not sure exactly. Yeah. I mean, historically, what this was first stated by Weil in his language, but I mean, this is the form that I saw in many textbooks. And
okay, okay. Because I look at the classical groups, I mean, there's no such statement. Maybe. Yeah, okay.
I'm not sure of this history. All
right.
But I guess most of the textbooks attributes this to Weil.
Okay.
Well, now, what if the unitary groups are not compact? Well, this is for compact unitary groups. Then what if this is they're not compact? Then we will have to think. So, well, the first question that we might encounter here is that, well, for non-compact unitary groups, how are we going to parameterize these representations? Well, for compact groups, we know that, well, we will have a very nice theory of say the highest weight theory, and well, we can parameterize them very easily. Now what if for non-compact unitary groups? And so the parameterization that we are going to take is the so-called Lawrence-Vogan parameterization, and I'm going to briefly explain it as follows. So for simplicity, I'm just going to consider the case of temporal representations and the non-temporal representation, but generic ones that can be reduced to this case. So so V is a Hermitian space of dimension n, and this pi is a irreducible temporal representation of UV. And the Lawrence-Vogan parameterization is given as follows. So to each pi, which is the irreducible representation of UV, we attach a pair, phi pi and eta pi, and where this phi pi is an L parameter, and this eta pi is a character of a abelian 2 group. All right. So what are they? So we say that a character of C cross is conjugate self-dual of sign +1 or -1 if it is of this form. Namely, it's like rotation, and this M counts how many circles that you go. And well, L parameter for unitary grouping n variables is a semi-simple n-dimensional conjugate self-dual representation of sign -1 to the n-1. Well, this is a pretty long sentence, but it just means that it's a direct sum of n characters. And here here I'm putting some multiplicity. Now, as phi, I put in the condition of being conjugate self-dual of sign -1 to the n-1. Now, what does this mean? Well, it means that any character that appears there, if that's not conjugate self-dual of sign -1 to the n-1, then it should appear in pairs. So explicitly, it means that if this m chi appears in phi and chi is not conjugate self-dual of chi is conjugate self-dual of the wrong sign, namely -1 to the n, then the multiplicity has to be even. And well, the same thing if it appears in chi and in phi and chi is not conjugate self-dual, then its conjugate should also appear like with the same multiplicity. All right. So in particular, if this would imply that the number of conjugate self-dual characters with the correct sign that appears in phi, well, of course, counting multiplicity, should have the same parity with that. And this is quite an important point. Even though it's quite small, it turns out to be important later on. So, well, now let's consider the Vogan packets. Say V, this is a formation space of dimension n, and phi, this is an L parameter for unitary groups in n variables. So to each L parameter, we can attach a finite set of irreducible temporal representations of UV, and this is the partition of all the set of all temporal representations of UV into a disjoint union of finite sets. And each of this, each of this is called an L packet, and the Vogan packet is just the disjoint union of these L packets for different Hermitian spaces. Now, I should stress that I'm taking the disjoint union for different Hermitian spaces, not different unitary groups. So sometimes you could encounter that the situation that Hermitian spaces are different, but unitary groups are actually the same. For example, UPQ and UQP, they are the same unitary group, but they are considered different inside here. So let's look at this example. Say pi, this is the irreducible temper principal series representation of u p plus 1p. And well, in that situation, if we look at the Vogan packets containing pi, then this contains two elements. Well, one is this pi viewed as a representation of this group, up plus 1p, and the other one is again this pi, but viewed as the representation of upp plus 1. So you see that there is some redundancies here in this Vogan packet, and somehow when we consider restricting problems, we need to consider like half of the Vogan packet. So we're gonna come back to this point later. So well, once we have the Vogan packets, well, remember that our goal is to parameterize all the representations. Now we have a parameterization of these packets, and then we need to parameterize the elements inside a Vogan packet. This is the internal parameterization, and well, this parameterization is given by that eta. So say this phi, this is it's a L parameter as before, and well, we can label these characters so that the first R of them are conjugate self-dual of the correct sign of sign -1 to the n-1, and we form this abelian 2 group. So these AIs are just symbols. It's really just labeling these components, and well, these Vogan packets, the elements inside a Vogan packet, would be in one-to-one correspondence with the characters from this abelian group A phi. So to a L parameter phi and a character from A phi, this is in bijection with another pair. This pair consists of a Hermitian space and an irreducible temporal representation of UV. Okay, this is the parameterization that we're going to take. So this parameterization depends on the choice of some weighted datum, and I do not want to talk about this choice because I do not want to confuse you. I myself get confused with this choice for quite a long time now. Now I do not want to confuse you. So, okay, now I want to talk about the restriction problems, and so first let's talk about the representation. So the setup is that we're going to consider two Hermitian spaces. One is of dimension n, and the other one is of dimension n plus 1, and say the W and B. And say pi is a irreducible temporal representation of UV, which is the big group, and sigma is the irreducible temporal representation of UW, that's a smaller group. So one subtle point here is that what do I mean actually by a representation? So by a representation, I really mean a smooth Fréchet representation of moderate growth, or the canonical Castleman-Wally globalization of a GK module. So I would point out that if you just work with the category of GK modules, this would not work. It is important that we put in the correct topology on these representations. We work in the correct category of representations. This is quite important. So the restriction problem is the following. So we have we define this so-called multiplicity, say pi sigma. This is the dimension of the UW invariant bilinear forms on pi tensor sigma. So previously we were saying that, well, we restrict our pi from the big group to the small group and consider its decomposition. However, because we are here looking at the infinite dimensional representations and the non-compact unitary groups and so on and so on, so it would be better not to consider that formulation, but instead this one. And this one is also compatible with the global application. So this is the multiplicity, and well, the multiplicity is at most 1. This is a really remarkable theorem, and the reference is here. This is proved by Sun Mingyu and Zhu Chengbo, and I think the Professor Zhu is here. So I'm very glad to be talking in front of you here. So I came across this theorem when I was in the graduate school, and around that time, at some point, I met Professor Zhu in Harvard, and he explained to me and many other students the key techniques in this papers, especially that final argument using eigenvalues. And I was quite astonished and said, "Oh, what a theorem!" And I like it very much. And well, that's the theorem, which basically says that, well, this multiplicity is either 0 or 1. Now the question is, well, when is this multiplicity non-zero? Well, it's either 0 or 1. Then you like to predict, well, when is 0, when is it 0, and when is it 1? Okay. Now here's the prediction. This is another remarkable book. I would say it's a book. It's a long paper by Gross and Prasad, and this is actually the content. The prediction of this multiplicity is actually the content of their conjecture. And I should also say that this book here is the introduction to me of this whole subject. I read this book maybe around like 2011 in the summer or something, and well, I read it from the first page to the last one, and I learned a lot from it. I like it very much. So here's the conjecture. This is conjecture 17.3. Well, I'm not gonna read this conjecture because I have to explain a bunch of notation here, but I would like to say that the theorem, so the theorem that I'm gonna present here in this talk, we're gonna is going to confirm this conjecture. So so let me state the theorem. So here's the setup. So we have two Lagrange L parameters, temporary L parameters. They are for unitary groups in n+1 variables, and this phi n is for unitary grouping n variables. And we have the Vogan packets like this. So two Vogan packets, one for UV and the other one for UW. And we have the centralizer. So it's a bunch of abelian elementary abelian two groups. So that's the setup. So the theorem. So the first part. This first part is usually referred to as the multiplicity 1 in a Vogan packet. So essentially, it says that inside a Vogan packet there is a unique member with the multiplicity being 1. Essentially, this is what it's saying here. But as we have observed before, Vogan packet, inside a Vogan packet, there might be some redundancies. So we got to be a little bit careful with this redundancy. And in fact, we need to cut this. We need to consider maybe just like half of the Vogan packets, and we do it like this. So we say that there exists a unique pair in the disjoint union of these L packets for different unitary groups, but we do not consider the arbitrary Hermitian spaces W and V. Instead, we insist that this W and this W and V, W is contained inside V, such that the quotient space V quotient by W is a line, which, well, of course, is a line, but we fix the sign of this line. Then this would cut this Vogan packet in halves. So it's essentially just half of the Vogan packet. So, and well, of course, you should really understand this statement as well. There is a unique member in this Vogan packet, which gives you multiplicity 1, and everything else will give you 0. Okay. Now the next part is to specify, well, which element in this Vogan packet gives you multiplicity 1, and here's the specification. So to specify which element inside the L packet, we just have to specify these characters from the abelian, the elementary abelian two groups. And here the specification is given by a bunch of local root numbers as these epsilons. And well, these epsilons are just some root numbers, and they're just plus minus 1. So actually this identity makes sense. And so let me make some remarks about these root numbers. So they depend on some choice of the additive character. And I said previously that, well, in the parameterization, in the nonlinear Vogan parameterization, we need to choose some data, some weighted data. And well, here, this local root number also depends on the choice of some additive character. So these two dependents would cancel each other. So finally, we get the correct statement. Now, second, these local root numbers can be made very explicit. So these local root numbers, they can be computed purely in terms of the long length, in terms of the L parameters. And these L parameters, because we're in the Archimedean place, these L parameters are just the direct sum of characters. So these local root number is just the product of the local root number of a bunch of characters. And for local root number for characters, we can make things very explicit. And if you want to find how explicit this is, and here we go. So this is the second part of the book by, again, Gross and Prasad, and this is called the examples. Again, I read it from the first page to the last one. I like it very much. And then it is proposition 2.1, which deals with with our situation at hand, and you see that this epsilon factor here where this local root number here is just plus minus 1. It's depending on the sign of this a, where this a is just that. Well, as you can see here, well, things can be made very explicit. So, okay, all right. So for the rest of the talk, I'll try to present a proof of this theorem. So now let me first mention some previous work. Well, many people worked on this problem before, and well, I'm just going to mention two of them. So one is this. So He Hongyu, he treated the case of the discrete series representations, and it is this paper. He basically proved the theorem for all discrete series representations. And the other one is the work by Raphael. Well, this is a really a big book, and he proved the so-called multiplicity 1 part, the multiplicity 1 in a Vogan packet, namely the first part of the theorem, using a completely different technique called the local transform. And this book is about 330 pages, and so it's a very long book, and it proves a lot of things. And in this book, it's a very significant work. When he was writing this book, we were at the Institute of Advanced Study in Princeton, and both of us were postdocs there. And he told me that, well, he told me at some point that, well, I think I can prove this, and say, oh, congratulations. And then he disappeared. He disappeared maybe for like 3 months or two or 3 months, and then. Basically, previously I can see him like every day, but for that 2 or 3 months, I could barely see him, maybe like once every 2 weeks or something. And he did not have haircut. He did not even shave. And well, eventually, by the time we left the Institute for Advanced Study, he finished this book. It's really some significant amount of work. And the following year, when I was in at Max Planck, I got a chance to read this book again from the first page to the last one. I should say that this book is well, even though it's very, very long, it's 300 pages, more than 300 pages. It is quite readable, and I in fact learned a lot of harmonic analysis from this book, and the results proved there are quite remarkable. And in fact, I'm gonna cite some of the results here to shorten the argument. But I should also say that the results that I would cite from here has nothing to do with the trace formula part. It's something that you need to prove before you run the trace formula machine. Right. So the main technique that I'm going to use is the theta lift. So what is a theta lift? Well, many I guess we got many experts here in the audience on theta lifts. Let me just say that this is the systematic and the explicit way to construct irreducible representations of one unitary group from another unitary group, especially from a small unitary group to get something on the big unitary group. Okay, and this is so explicit that we can study it quite easily. Now, the relation between say here, suppose we start from some representation pi prime of a small unitary group, and we obtain another representation, say pi. This is the representation of the big unitary group. Say the relation between the Lorentz-Vogan parametrization of pi prime and pi can be made very explicit. Well, in our particular case, namely the real unitary groups, this is the work by Paul, but in fact this is the work of many people, and we have a similar statement even for p-adic unitary groups, and this is the work by Gain and Ichino in many of their long papers. It's eventually it was proved in where it's WeTech, which one was it eventually proved for p-adic unitary groups?
I think it's the one called Gross-Prasad conjecture and local Theta correspondence.
Yeah,
I think it's a 2016 paper.
That name just slipped from my mind. I could only recall that it's an inventionist paper, but
yeah, we had two. The first one was called formal degrees and local Theta correspondence, and there I think we proved part of it, and then we completed the rest in the next one, which is called Gross-Prasad conjecture and local Theta correspondence.
Right, thank you. So, well, of the explicitness of this construction, this turns out to be very useful in the study of the branching problem. But the sad news is that, well, not all irreducible temporal representation of UN+1 can be constructed from smaller unitary groups, in particular UN. Not all of them can be constructed. Some of them can, and some of them cannot. Well, now here comes maybe the key observation. So the key observation is the following. So which of them can be constructed and which cannot? So say pi, this is a irreducible, representation of UN+1. So can I annotate here? Maybe I can. Maybe I can annotate here. Can I annotate? Well, maybe not. I don't think I can annotate. But anyway. Well, this pi is a irreducible representation of UN+1, and it has some Lorentz parameter. Now, we do not try to construct this pi directly. We try to construct this pi up to a twist of the determinant character. Well, if we allow this flexibility, then the many of them can be constructed. Well, in fact, if we look at the work by Paul, then up to the twist of the determinant character, this pi can be constructed from the theta lift from a small unit from some unitary group in n variables if and only if the L parameter here contains this chi0, which is the conjugate self-dual character of -1 to the n. So as long as the L parameter contains a conjugate self-dual character of sign -1 to the n, it can be constructed from a smaller unitary group up to a twist. And in fact, not just that this representation itself can be constructed from from a smaller unitary group. Basically, this whole packet can be constructed. Well, of course, again, up to twists by the determinant characters. We have to allow this this flexibility.
Excuse me.
Yes.
Can I ask a question? By twisted, by twisted by the determinant, are you mean you work on two cover of the unitary group?
No. Well, unitary group the center is U1.
Oh. Okay. Thank you.
No. Well, I mean, twisting the say. If we were in the case of discrete series and we got some Harry general parameters, then twisting by the determinant essentially does the job of shifting these characters by 2.
Mm. Okay, thank you.
So now this is the case where we have one conjugate self-dual character of the correct sign. So now what we actually need is that, well, if we have 2 conjugate self-dual characters of the correct sign, then we can construct this representation up to a twist by a composition of 2 theta lifts. So say we got some pi here on uv, this v is n+1 dimensional. Then we can find 2 Hermitian spaces v0 and v prime. This v0 is of dimension n, and the v0 is of dimension n-1, so that we can find some representation here on the bottom level, this uv0, and we take a theta lift and twist, and then take another theta lift, then twist, then we get this pi. So up to a twist, we can do a lot of things. Right. So, well, why this flexibility is allowed? That's quite interesting. But well, in fact, it took me a while to realize this point. I overlooked this for quite a long time at the beginning. Namely, this multiplicity is insensitive to the twist. So if you twist one by the determinant to the k and twist the other one by the determinant of -k, then you basically get the same thing. Well, just because of this, well, you restrict the determinant of uv to the determinant to uw, then you get the determinant of uw, and that's what it is. This is the reason why we can just construct things ignoring this twisting. This twisting is harmless. This is I mean. This proof is full of these overlooked points. Each of them took me quite a while. For example, this one, when I realized this for the first time, I was walking around my house and say, how come that this is true? And I walked around for like 1 hour, and then I realized, oh, come on, it is true. Okay, now once we have this this theta lift, we can do the usual seesaw argument. This is a very familiar seesaw argument. So let's assume that this say we're still looking at pi and sigma, and the parameter, this phi for pi, contains A conjugate self-dual characters of the correct sign. And this the L parameter phi sigma contains B conjugate self-dual characters of the correct sign. Now let's assume that A is bigger or equal to 2. So So we are in the situation where we can do theta lifts. So now a very familiar argument, but now you should apply it twice. Would tell you that this multiplicity pi sigma, this is the same as the multiplicity of the sigma 0 and pi 0, where the sigma 0 is a irreducible representation of some un, and this pi 0 is a irreducible representation of some un minus 1. So here I write un just as to say that this is a unitary grouping n variables and might or might not be compact. So this is the seesaw argument, and the important part is that we obtain some other representations with the following property. Well, they are on smaller unitary groups, yeah, true. But what we care about is that we are actually reducing the number of conjugate self-dual characters of the correct sign. Namely, this pi 0, this contains a minus 2 conjugate self-dual characters of sine minus 1 to the n, and this guy, this phi sigma 0, contains the same number of conjugate self-dual characters of sine minus 1 to the n minus 1, namely b. So eventually, so if you look at the left-hand side, this pi and sigma, the number of conjugate self-dual characters of the correct sign previously it's a plus b. Now on the right-hand side, it's a plus b minus 2. Okay, this is a really, really important observation. We're going to make use of this later. Okay.
Xie-Hang, could I ask a quick question?
Yeah.
So pi is on un plus 1, sigma is on un, right?
Yeah, right.
And sigma 0 also on un.
Right.
Yeah. Okay. The relation between sigma 0 and sigma, is it just a twist by determinant or more sophisticated?
I'm not sure if that's just a twist, because you twist and then take the theta lift and then twist and then take theta lift back. You might not get the same thing.
Okay, so but the data for this sigma part is from un to un basically.
Yeah, right.
Yeah.
Yeah,
okay.
exactly.
Thank you.
So now here's the proof of the theorem. Let's actually get to the proof. So here comes the trick. So recall the setup. So we have two parameters, this phi n plus 1, and the other one is phi n. And we have two Vogan packets, this pi phi n plus 1, and the other one is pi phi n. And we'll say pi is inside the pi is the representation of the big group, and sigma is the representation of the small group. And they each correspond to some character of the abelian 2 group called eta pi and the eta sigma. Now we assume that this phi n plus 1 contains a conjugate self-dual characters of sine minus 1 to the n, and this phi n contains b conjugate self-dual characters of sine minus 1 to the n minus 1. Okay. Now the trick, this is perhaps the most important part of the proof, is to realize that we do not do the induction on the size of the unitary group, but we do the induction on a plus b. This is quite counterintuitive from my point of view, and it took me quite a while to realize that we can do it like that. Well, it's just a trick, and it turns out that this is a very nice trick, and it works. And it's going to make the argument extremely short. So we should first observe that this a plus b should be odd. Why? Because we are counting the number of conjugate self-dual characters of the correct sign in the L parameter. So A should be of the same parity of n plus 1, and B should be of the same parity with n. Therefore, A plus 1 should be of the same parity with 2n plus 1, which is odd. Okay. All right. Now, what we do the induction on A plus B. So the basic case is A plus B equals 1. Now assume this is the case. Now in the situation, well, pi and sigma are both irreducible principal series representations. Well, and this eta pi and eta sigma are both trivial. So, and then the local root numbers are all 1. So in this case, well, the multiplicity is quite straightforward to compute. Well, the multiplicity equals 1. Well, the simplest way to see this is that, well, the tempered intertwining equals 0. What is this tempered intertwining? Well, in fact, what you can do is that you can find V1, V2 inside pi, and W1 and W2 inside sigma, so that we take this integration of matrix, and this is not 0. And now you just observe that if we fix V2 and fix W2, fix this V2 and fix this W2, then as linear forms on V1 and W1, this is UW invariant. Therefore, this gives you the linear form that you want. And well, to see this, well, the most straightforward way is to cite the result of Raphael. He calls this the tempered intertwining in his book, and he has something called he has a section maybe in chapter like 8 or something called the parabolic induction and the explicit tempered intertwining. And well, a small induction will tell you that well, this is true. Well, there are plenty of ways to do it. These are just irreducible principal series representations. So you can do it in whatever way that you like. But perhaps this is the shortest cut.
Oh, so Xiaohang, so this is the convergent, right?
Yeah, because everything is tempered.
Temper. You don't need to do any regularization or anything.
No.
I mean, it's already okay.
No, you do not have to do anything.
Okay.
This is codimension 1.
Okay.
Codimension 1 tempered. You do not have to do anything.
Okay.
You just take the integration of matrix coefficient.
Mm-hmm.
It works.
Okay.
Well, that's the base case. So A plus B equals 1. Now we know that, well, A plus B has to be odd. So let's try the case, say it's at least 3. And therefore, either A bigger or equal to 2 or B bigger or equal to 2. Okay. Now let's do A bigger or equal to 2 first. So recall that A stands for the number of conjugate self-dual characters of the correct sign for the big group. Okay, let's do this first. Now, once we have this, so the big group contains enough conjugate self-dual characters, then we run the argument of Seesaw as before, and we end up with this equality of the multiplicities, where the sigma is a irreducible representation of some un, and this pi 0 is irreducible representation of some un minus 1. But as I said, we do not do induction on the size of the group, but we do the induction on A plus B. So this phi pi 0 contains, so phi pi 0 is the L parameter for pi 0. This contains A minus 2 conjugate self-dual characters of sign minus 1 to the n. And the L parameter phi sigma 0 contains B conjugate self-dual characters of sign minus 1 to the n minus 1. So now on this side, the number of conjugate self-dual characters of the correct sign is A plus B minus 2, and we are good by induction. So the theorem would hold for sigma 0 and pi 0 by our induction hypothesis. And sigma 0 and sigma related by theta correspondence, pi 0 and pi sigma, pi 0 and pi, they are related by theta correspondence. As I remarked before, the parameters can be computed, their parameters can be computed explicitly. So a little bit of computation will tell you that the theorem holds for pi and sigma. Okay, this takes care of the case A bigger or equal to 2. Now, what if B bigger or equal to 2? Now we need to make use of another trick. Now, this trick is the following. So this is called the induction and multiplicity. So the trick, so B stands for the number of conjugates of dual characters of the small group. But the trick is that we use parabolic induction to enlarge the small group. So let's consider this. So W is contained in V, and let's do another one called W plus, where this W plus is W the orthogonal direct sum with a hyperplane. And P, this is a parabolic subgroup of this U and W plus. So this is a unitary group in n plus 2 variables. So this is U n plus 2. So this is a parabolic group whose Levy part is C cross times UW. Okay, and then we form the parabolic induction like this. So on this C cross part, we just take the absolute value to the IT, where T is a real number. And the sigma is a irreducible representation as before for this UW. Okay, let's form this parabolic induction. And now for generic T, we have this. The multiplicity would not change. I think even not for non-generic. I think this even works for any T, not 0. I think it works. But let's say just for generic T, this we have this. So the multiplicity would not change for generic T. So recall that on the left-hand side, this is UN, this pi is UN plus 1, and this sigma is UN, and this on the right-hand side is pi is again UN plus 1, and the sigma plus is UN plus 2. So now we should note that the sigma plus, the parameter of the sigma plus can be computed fairly easily. So phi sigma plus, this is just the phi n direct sum with an absolute value IT and absolute value minus IT. And this parameter, this eta, the internal the packet itself would not change, and this parameterization, the internal parameterization would not change.
Johan, I have a simple question. Is this equality or multiplicity also a very special simple cases of seesaw?
No, this is not. Again, you can deduce this from that temper and the intertwining.
Mm-hmm.
It's all about this parabolic induction. Well, you can do there are many ways you can do it. You can either go through the temper intertwining inside the result of Raphael, or you can just do it by hand using all the orbit method.
Yeah. So I think Chenpo, you have a paper with Bing Yong and Di Hua, right? That do this, like bound the multiplicity of Bessel functionals for induction in terms of the Bessel functionals on the inducing data.
Right.
It's basically that argument.
Okay.
I think that's what I mean by doing it directly, right? By is using the Mackey theory, right? And
okay. Okay. Got it. Yeah.
Well, now here comes the final step. Now the final step is, well, the case B bigger or equal to 2. Now assume this. Now we'll just take any T and consider this induced representation. So now the point is that now we got a big group, which is UN plus 2, namely this W plus, and we applied the previous case, namely A bigger or equal to 2 case, to the pair sigma plus and pi. Now the trick is that now here B bigger or equal to 2, and now in this situation, this B becomes the one for the large group. So we can apply the previous case. And because the multiplicity will not change, and the parameters can be calculated just fairly explicitly, so we know that theorem holds for sigma plus pi, and this would imply that theorem holds for pi and sigma. And that's it. Okay, that's the end of the proof. It's a very